Hi, everyone. Thanks for sticking around for the final few talks. My name is Eric Thiessen. I'm a postdoctoral researcher here at Laurentian with Metal Earth, working with Bruno Lafrance and Steph Perrotet. I finished my PhD, I guess, 2 years ago at Simon Fraser, and fortunate enough to be starting up at Memorial next year. So yeah, if any of this work is interesting to anyone and would like to continue collaborations, let me know. So yeah, my talk and my research project is on the westward extension of the Porcupine-Destor Deformation Zone. And for those who may not be familiar, this is the same one that hosts the large gold camp in the Timmins area. So far, academic partners is myself with Metal Earth and Laurentian, but we may join forces with industry and government soon. So I'm going to give you a quick regional context of where my project is and what it entails. And as well, I'll give you a brief overview of the fault systems that I'm looking at. And that will give a nice transition into what the Western Extension project is and hopes to achieve. And from there, I'll share with you new and preliminary results from my field work this last summer, summer 2020. From both the North Swayze Greenstone Belt and the Kapuskasing Structural Zone. So regionally speaking, we're in the Abitibi Wava terrain in the southern heart of the Superior Craton. And as you can see, my project will hopefully involve not only the Abitibi and Kapuskasing, but also the Wava terrain. And Nicholas gave a great introduction to the Kapuskasing, and I'll just reiterate here that the Kapuskasing is a very interesting deep crustal exhumed feature that is that runs against the grain of the typical geologic and structural evolution in the Wava and Abitibi, and it exposes deep, mid, and lower crustal rocks that were undergoing metamorphism and tectonism at the same time the upper crust was developing these shear systems and depositing gold. So looking in on part of the Abitibi terrain, this is immediately east of the Kapuskasing. We can see these two prominent structures that run through the Greenstone Belt. To the north, we have the Porcupine-Destor Deformation Zone, and the southern one is the Cadillac-Larder Lake Deformation Zone. And you can see the distribution of orogenic or lode gold deposits is very strong along both of these breaks. And as you go west, towards past Timmins and into the Swayze, you see fewer deposits, but they still exist, and even fewer as you go west, although of course there is the Borden deposit in the Kapuskasing. So here I'll give you a quick overview of what these fault systems are generally thought to be and how they are thought to form. First off, after predominant volcanic activity and formation of all these volcanic terrains that we know and love, we start to get accretion and synorogenic activity, and this includes an early phase of synorogenic extension. And this is thought to develop deep-seated normal faults that tap as far down as the lowermost crust and uppermost mantle. And this process is also thought to be involved in bringing tapping the mantle and bringing up some of these alkaline intrusive systems like lamprifiers and alkaline cyanites, for example. This time frame is also broadly thought to coincide with the beginning of coarse molasse or style sedimentation, these coarse conglomerates that we see filling these Temiskaming style basins, as they're called. And of course, this then is the second stage of this development. Begins with an inversion of these basins and a reactivation of these normal faults into thrust sense faults. And it's this phase that is generally thought to bring up deep-seated fluids and gold into the upper crust. This is obviously also the phase that would be involved in burying and synorogenically creating more of these polymicted conglomerates that we generally call Temiskaming type. And then after that, broadly in the same spatial region as this fault activity is going on, we then develop these broadly strike slip features. And this would be the equivalent of this, what you can see in the diagram, the blue lines. That would be the Cadillac-Larder Lake and the Porcupine-Destor fault zones that broadly overprint this region. And this is where most of the gold deposits tend to be focused around or in. And it's very likely that this later stage strike slip deformation is involved in remobilizing and upgrading deposits, even if they may not have brought up the gold initially. And of course, there's a late stage of exhumation that may not have anything to do with the gold, except for perhaps preserving it or not preserving it. So again, an overview of the Western Extension project here. I've highlighted the very gold-rich endowed portions of these shear systems in yellow. And as we move west into the Swayze, Kapuskasing, and Wawa in blue, we can see these are the regions that have a much less well understood tectonometamorphic history and less, generally speaking, less gold endowment. And so a broad overview of what this project is it aims to compare fault zone processes in the Abitibi, Swayze in particular, Kapuskasing and Wawa terrains. And some of the methods I have been and plan to employ are structural and kinematic analysis of these fault zones, and better understanding these synorogenic basins, both the timing and provenance of them, age and chemistry of intrusions, and the style of mineralization as well. So here's a close-in field map of my general field area for this last summer. I was able to spend approximately 3 to 4 weeks in the field with an assistant, so just the two of us, and we spent most of our time in the North Swayze greenstone belt that's highlighted there, and then we also spent some time in the middle part of the Kapuskasing. This is broadly in the Kapuskasing. I spent a lot of time between where Nicholas spent a lot of his time, so hopefully this will be new, interesting data that complements his. But I also have collected some samples from the South Kapuskasing, which I'll get to later. Zooming in a little more to the North Swayze, the purpose of this slide is to give you a very brief overview of the geology of the region. There's two main deformation zones that I've highlighted. The northern one is called the Slate Rock Deformation Zone, and the southern one, I'm just going to call it the Porcupine-Destor Deformation Zone for now. This southern Porcupine-Destor zone has been worked on seismic and MT work through Metal Earth by Rasmus and Tom Gemmel and others. And this is the proposed location as of lately for where this structure probably exists in the North Swayze. On the right, I have general ages of the volcanic assemblages. The top or the northern package is generally around 2715. The southern package is around 2700 MA. And then there's a few isolated pockets of 2730, so it's a Deloro-aged volcanic assemblages. And of course, there's this central basin in the North Swayze that's in gray, the gray polygon there. Largely previously thought to be associated with porcupine-aged and porcupine-style sedimentation, but there's recent work that has suggested there might be Timiskaming-style clastics here as well. So the exposures in the North Swayze were actually quite poor, unfortunately. Typical exposure as illustrated on the left, covered in moss and lichen. You can get some information from this, but very detailed structural observations can be difficult. So the best areas that we focused our time on were road cuts, of course, and some recent strippings that GFG Resources and some other industry folk had cleaned off that made for much cleaner and nicer observations. Now, the next thing I want to do is show you some of this preliminary field and analytical data from the North Swayze, broadly following what we know of the tectonometamorphic history for regions like Timmins and some of the other better known gold endowed portions of these fault systems. So I'm broadly following that framework and hopefully providing some robust age constraints on these deformation episodes, but I hope to also make them even better and test some of this. So first, I believe we may have evidence for some of this early synorogenic extension. We get this in both the northern Slate Rock and the southern Porcupine-Destor fault systems. And we have pretty clear south side down, north side up shear sense indicators. Although some of these these faults are very steep and some may be overturned, so it's not 100% clear if this is truly related to extension or not. But some of these kinematics are deforming quartz feldspar porphyries that have ages between 2690 and 2680. So if these are extension-related structures, an upper age limit on when this is happening is around 2690 to 2680. Now, also during this extensional phase, there's the proposed lamprifier and alkaline magmatic episode. I was able to find two different suites of lamprifiers within the North Swayze. You can see in the upper geochem spider plot, you can see there's two distinct types of lamprifiers there. The ones with the solid black circles, the large ones, those have an obvious elevated niobium tantalum anomaly, and those ones were dated at about 1100 or so MA. Those are associated with the mid-continent rift likely, and that age in geochemistry has been well documented before, especially in the Wawa region. But of course, there's the second type of lamprifier as well, and this is with a much more depleted niobium tantalum anomaly and as well lower titanium. And I was able to only date one of these lamprifiers so far, actually, that I obtained from the Matheson area. That was a really nice age of 2686. But I have similar lamprifiers from the North Swayze with the same geochemistry, and really hoping to get some more robust ages from those to confirm that we have this age of alkaline magnetism in the North Swayze, although it seems like we do. So evidence I have for the proposed next stage, the basin inversion and reactivation of these faults, is really only at the moment coming from these deposition of these coarse clastics, alluvial, fluvial, polymicted conglomerates. The upper left image, you can see abundant rounded clasts. The white ones, that's all altered feldspar, predominantly quartz feldspar porphyry clasts. But there's also altered mafic clasts, chlorite fuchsite looking clasts, and some small chips of iron formation found in there as well. And we've been able to date 4 new samples of this coarse, of actually sandstone layers within this coarse clastic sequence. And we have ages that's maximum ages that span as old as 2690 and as young as 2670 MA. So at least from a superficial view, it seems to indicate that we probably do have at least Timiskaming aged and looking sediments here, which help conform to the model known farther east. But ongoing work with Rasmus Haugard and Tom Gemmel on the actual details of the lithotectonic stratigraphy here will help confirm that. So the next phase of deformation in the North Swayze is much more enigmatic and hard to put your finger on. This is a magnetic map of the region, and you can see some various magnetic contours going in and out of these large shear systems in the north and south. And there's some good indication that these are predominantly left lateral structures. Although in chatting with some of the company geologists in the region who've seen more of the rocks than I have, admittedly, they seem to think there's also a dominant right lateral component. And this could be either 2 distinct phases or, of course, dealing with a transpressional system. And so far haven't been able to work out the intricate details of that. And this is just some pictures of some of the deformation in the slate rock deformation zone. We clearly have right lateral and left lateral structures. On the left, we're actually deforming some quartz carbonate veins. And in this case, these veins contain arsenopyrite, tourmaline, and gold, very similar to some of the more prospective veins seen in the Timmins mining camp. There's also quartz carbonate veins that host gold roughly more central in the North Swayze that generally trend to the northeast or strike to the northeast, and these are much less deformed as they haven't been brought into these major deformation zones. And in fact, internally, they have almost no deformation microstructures at all within the quartz and calcite. And on the left image there, you can see some rusty alteration. I haven't confirmed whether or not that's anchorite or not, but that seems to be a common feature. So going back to these gold occurrences, in the various diamonds are various gold occurrences that GFG Resources has noticed, and many of these prospects have been drilled. So they're seeing this gold both in the major shear systems as well as in between the two. I was able to sample you can see the star there. It's on a northeast striking, southeast dipping, fairly undeformed vein, quartz carbonate vein with late gold in arsenopyrite fractures. And so I was able to get that arsenopyrite sent to Rob Creaser for rhenium osmium dating, and he was able to send me a result back about an hour ago. So I haven't really had time to interpret this, but it's much older than expected. It was about 2733. So this doesn't really conform to the model, but it also doesn't refute it either, because what we may be seeing here is we may actually be dating older arsenopyrite that literally just predates the gold by quite a bit. And so I really need to, this is my first time working with the rhenium osmium system, and especially model ages, so I don't want to be too confident in what this age means, but I don't think it's dating gold. I think it's at the very least predating gold, and a lot more detail needs to go into understanding this age. And of course, very late in this history, there is evidence, especially in very fine-grained micaceous metavolcanics. We have these near horizontal crenulations, which are probably associated with a late-stage exhumation of the entire region. And again, this conforms pretty well to what is seen elsewhere, for example, the Timmins area. And so I've put up this data to plot it on the time x-axis here, comparing it with the Timmins region. This is comparing it with data mostly from Benoit's 2017 overview paper. And so in the North Swayze at the bottom there, you can see some hollow symbols with white interiors. Those are from previous data, either from quite a while ago or recent data acquired by the OGS. And the data that I'm contributing in this talk is colored in, so the various bold colors. And so early on in the orogenic history, we have these porphyry systems, and we also have coarse conglomeratic units that are very similar to Temiskaming style deposits. And this is happening around 2690 to 2680 or so, and even a little younger for the conglomerates. Mineralization age is still quite unknown at this point, but it's likely to post-date most of the syn to post transpression. But overall, it seems to compare very favorably with what's seen in the Timmins area. So future work and ongoing work, I'm tacking on to a project that was started a few years back with Rasmus and Tom, looking at the synorogenic basins, better understanding their age, provenance, and tectonic setting. And then the second major focus is putting together all these regional tectonic features from the deformation history, cross-cutting plutons, lamprifiers, gold mineralization, and trying to understand the overall tectonic evolution, how it compares to other gold endowed regions to the east. And of course, the other half of the field work this last summer involved the Kapuskasing region. And so I just want to quickly point out on the southern part of this map, I have labeled the Cadillac-Larder Lake Deformation Zone. In this area, it's referred to as the Ridout Deformation Zone. And it has about a 25 to 30 kilometer offset with the Borden belt, which is thought to be the logical continuation of that deformation zone, which links up with the Borden gold deposit. Of course, both the Borden gold deposit and the Ridout zone contain not only gold deposit, but Temiskaming style conglomeratic units as well. So using broadly the same logic, assuming that similar amount of offset may have happened at the North Swayze, about 25 to 30 kilometers up the Ivanhoe Lake fault zone, we have this distributed zone of high metamorphic rocks and shear, although this shear is documented throughout the entire Kapuskasing. And this could be it's not going to be a localized fault zone, but it's a good region that I focused in on to try to better understand the tectonic metamorphic evolution in this part of the Kapuskasing and compare it with the Swayze. Broadly speaking, very high grade rocks in the Kapuskasing. Nicholas did a great job showing what exists there. The top left shows some OPX grade P-lites. OPX is generally a paratectic phase within leucosomes. We also have paratectic garnet in leucosomes and these straight banded mafic gneisses on the top right. Rarely preserved, but they do exist, as we have these very anhydrous garnet CPX mafic granulites. These are rare in the Kapuskasing because there's such a predominant hydration and metamorphic event later on that has rehydrated much of the region. And on the bottom right is just a nice image of that major anorthosite complex. So I'll divide it up to show you some of this preliminary data from the North Kapuskasing region and compare it to the Borden belt, where I also collected some samples. These are metasedimentary units. On the left, you can see these are the mixed peelite and semi-peelites. These are some of the OPX grade migmatitic rocks. And they have a max depositional age broadly between 2680 and 2660. So very favorable and comparable to what we see elsewhere in the Swayze and Timmins region, although I wasn't able to find any bona fide conglomerates in these units. Now also there's metamorphic zircon and monazite that I've been able to date. That shows a very clear prograde peak and retrograde cycle between about 2665 and 2640. Now, deformation in this northern Kapuskasing region, this has been documented before, but I saw it as well. There's an abundant left lateral shear in these broadly east-west trending structures with a shallow west dipping lineation. Really nice CS fabrics within migmatitic rocks. We have S-folds of various dikes, and we have left lateral rotated winged porphyroclasts. And where these were, I was able to date these, it broadly corresponds with peak metamorphism in this North Kapuskasing region to edging in towards the retrograde part of the metamorphic history. So that's broadly 2660 to 2645 for this left lateral shear. Now in the southern Kapuskasing, of course, we have the Borden conglomerate, which I wasn't able to date as well as Tom Crow did initially. I had a max age of about 2680. He had an age of about 2668. But I sampled a number of other meta greywackies and peelites farther to the east along the Borden belt, and these are high-grade peelites. And I was able to get max depositional ages around 2660 to as young as 2630. And that's a pretty significant result that I'll explain in just a minute. So here, plotting the Kapuskasing data up with the North Swayze and Timmins, one thing that's obvious is we seem to have these old metasedimentary units, which of course already was known for the Borden belt, but we seem to have these rocks in the northern Kapuskasing as well, deposited around 2670. And then we seem to have this very well-constrained metamorphic cycle, at least in the North Kapuskasing, between 2660 and 2640 of burial, prograde, peak, and retrograde metamorphism. The interesting thing here is in the southern Kapuskasing, I was able to find much younger sedimentary depositional ages, as young as 2630 in one case. And one of the really interesting things about this is this does correlate with one of Tom's older models, looking at these young metamorphic ages in the Kapuskasing and suggesting it has to do with continued underplating of sedimentary material. And we seem to have evidence, at least in the south here, for not only deposition, but also burial and rejuvenated migmatization and probable fluid generation in the lower crust at this time. And so this is an interesting first order observation that I've been able to see, where we have this older history in the North Kapuskasing, which is much more similar to what we see regionally in the Abitibi, peaking around 2660. And then we seem to have this prolonged event happening in the lower crust in the south. And I'm not sure if this, at this point, it's all speculative. I don't know if this may relate to some of these young xenotime or monazite ages some folks are getting related to gold in the southern region, but it would be really interesting to chat with those of you that have worked here for much longer than me to see if this could make sense. I know John already spoke earlier about how that would make sense. And I just threw this in at the last minute after hearing Antoine's talk, just to show that there is some trace element in zircon data to suggest that the North Swayze and Kapuskasing sedimentary rocks, at least using these parameters, have very similar magmatic arc affinity and may be sourced from similar volcanic rocks. And so I don't know if you and Doug or anyone want to talk about this later, but you may want to think about using Swayze sediments and potentially Kapuskasing sediments as well in your study of gold mobilization in metamorphic fluids, as long as it works with Nico's project. So for future work, of course, I'm going to focus on these metasedimentary rocks, understand their tectono-metamorphic evolution, compare them with other gold-endowed areas in upper crustal shear systems. And also, I hope to look at some of these more dehydrated mafic granulites to better understand when they initially were metamorphosed and what their thermal history was, to really understand if we did have long-lived deep crustal thermal evolution, or potentially many thermal pulses that aren't necessarily recorded very easily in the upper crust, but may be significant in terms of gold remobilization. Okay, with that, I'll just end it there because I think I'm running out of time. So you could read the conclusions if you want, but I'm happy to take any questions from anyone.
Great, thanks everyone. Is there any live questions for Eric?
It's Mike here. I had one. Eric, I wondered why you thought that that trend on the uranium, ytterbium, niobium, and terbium plot was an arc array rather than a trend from mantle type sources up toward continental crust, in other words, AFC.
I mean, that is possible. This is literally just plotting it on one of the discrimination diagrams that from a Grimes 2015 paper that looked at a lot of zircon trace element data. I mean, it is possible, but I would assume that some of these zircon trace element compositions would actually go as far down as hitting the mantle array if they weren't as contaminated, and that would give some indication that we actually have less evolved material, but I can't say for certain.
If you look at the equivalent diagram in Julian Pierce's paper in 2008 that uses niobium instead of thorium instead of uranium, you'll see his emphasis is on the trend and not exactly where it lies. So the trick is the trend, because if you look at all his examples, of which he has very many, of actual arc magmas, that they're all subparallel to the mantle array and displaced quite a lot.
Okay, thank you for that. Yeah, I'm not married to that interpretation. I was just mostly trying to show that they're similar.
A lot of people bandy around arc signatures in these rocks, and I guess I'm subduction hesitant. Yeah.
Eric, it's Phil here. I'm looking at this last slide of yours and wondering whether you have attempted to extend the structure any further west or not.
Well, I haven't been able to attempt to due to field timing constraints. The hope is to extend this project farther west as it continues.
I mean, there are gold deposits at Wawa, and I'm sitting here wondering whether there is a connection or not.
Absolutely, and there's been some early work postulating this exact connection and lining up some of these major structures across this region. And so part of this project is tapping into those early ideas of, do these fault zones connect?
Thanks for that.
Okay, thanks very much, Eric.